So most of the trig problems we've seen are just for two-dimensional things, but the real world's not two-dimensional. So let's look at some three-dimensional trig problems. The problem is it's a lot easier to look at two-dimensional figures than three-dimensional figures. So often what I do is I'll get the three-dimensional picture, but I'll redraw it in lots of different two-dimensional diagrams so I can get my head around what's going on. And sometimes you might end up drawing triangles that aren't actually drawn in the actual diagram itself. You create these new ones to help you out. Sorts of questions. If you're in two dimensions, how do you find the angle between a line and a plane? So a flat surface, and you've got some sort of line going into that flat surface. So for the sake of an example, we'll look at this. It's a cone. And you can sort of think of that as that situation. The base of the cone is a surface, and just the cone doesn't really have an edge, I guess, but if you imagine it having an edge, if we were to draw the cross section, you've got a line coming into that surface. We want to find the angle that this curved surface makes with the base. So in other words, it's this line that I've labelled 15. What angle does it make with the base of the shape? So when I've got that situation, we drop a perpendicular from any point on that line down to the plane. And I guess it's convenient to use the vertex straight down. So I'll drop that down. And this now creates a right angled triangle in two dimensions. If you imagine cutting that cone in straight down there, you've got this right angled triangle. You join the point of intersection of that line you drop down along to the plane. Now, conveniently, because of the shape I've got, that's the diameter of a circle. I've already got that line there. And it's half the diameter, so it's a simple right angled triangle trig problem. So 9 over 15 would be the cosine of that angle. Okay, 53 degrees, we've got the answer. The other thing we could be asked to do is to find the angle between two planes. So like you've got two sheets of paper, if you like, meeting each other. What angle do they make with each other? So that's another common type of question. So I've got a tetrahedron. So all of those faces are equilateral triangles in a tetrahedron. Or a triangular pyramid, I guess, is another way of describing it. We want to find the angle between two of the faces. So we've got two planes joining together at an edge. So how do I do this one? The edge is the line of intersection between the two planes. So what I end up doing is from a point on that edge, I draw perpendiculars along both of the planes. Now again, for convenience here, I'm going to choose to go from the point here, which will go through the vertex. And I guess the reason I'm doing that is because I know dimensions of the shape, so I can work out the length of that line. Then from E, it would also go through this vertex as well. So I've drawn in perpendiculars along the plane from that point of intersection. That's the angle that I'm trying to find in that triangle there, triangle AED. That's the angle I want. This is where, okay, I'm going to redraw this in two dimensions to make it easier for myself. There's my triangle. I know AD's length A because it's a tetrahedron, so all those edges are the same length. I've got to find theta, so I'm going to need some other sides. This is where I'm now going to redraw the base. If I look at the base of that triangle, the dotted line is the perpendicular height. But I know that angle is 60 degrees because all of those triangles are equilateral triangles. So that's 60. A again is the edge. Well, I know AE then will be A times root 3 on 2. I could use trig to do it, or I could remember the ratio in that 30-60. Remember the special 30-60 triangle where the sides went 1, 2 and root 3? So all the sides will always be in that ratio. However I do it, I can work out that length, AE. So I can use trig, or I can just use similar triangles, whatever. So that's what I say. So I'm using the fact that they're in the ratio 1, 2, root 3. I'm actually going to need the cosine rule to solve this problem. Now we'll look at the cosine rule again in a couple of days' theory, but hopefully you remember what the cosine rule is. So I sub into it. Cos theta will be 3a squared, so I'm going back to this one now. Both of these dotted blue lines will be the same length, because remember these triangles are all the same size. So it'll be 3a squared on 4 plus 3a squared on 4 minus a squared over 2 times a root 3 on 2 times a root 3 on 2, which all of that tidies up to simply be 1/3. So cos theta is 1/3. I now know the angle between them is 70 degrees 32. Let's look at an HSC one. It goes back quite a while. So a surveyor is standing at the point A. It's due south of a tower. Tower's height H. We've got the angle of elevation, so look up, 45 degrees. The surveyor then takes a walk over to point B, which is 100 metres due east, from where she then goes and measures the angle of elevation. It's now 30 degrees. Express the length of OB, so OB, that length there, in terms of H. I'm just going to draw a triangle that involves OB. So that is the triangle OBT. I'm using that one because I've got some information. I know that's 30 degrees. They want it in terms of H, so I can get H in there. So OB over H will be tan of 60. So it's H tan 60. I mean, it's probably good enough for an answer. I suppose we could work out tan 60. It's one of our exact values. So it'd be square root of 3 times H. I could have written that as well. Show that H turns out to be 50 root 2. Well, that's when I drew another triangle that also involved H, and that was this one, AOT, and that angle was 45 degrees. But that's nice because that's a 45 degree right angle triangle. Again, we've got exact ratios that can help. It's isosceles, so I know OA, or AO, is also H. Now, I've also got this triangle. So AB is 100 and OB is H tan 60, which we just worked out in part I. So I've got that one. And I could use Pythagoras on that one. So H squared plus 100 squared is H squared tan squared 60. Playing around with this, we get our H is 50 root 2. Okay. So I used the first triangle to work out that AO was also H because of the isosceles triangle. I then used the triangle that was sitting on the base of the picture to use Pythagoras and got that answer there. Calculate the bearing of B from the base of the tower. Going to draw a picture up again. Bearing of B from the base. O was the base of the tower, so that's where I'm putting my compass. The bearing of B. B was over there. We just worked out that that was 50 root 2. AB is 100. I'm trying to find that angle there, basically. That would be the bearing. I can work out angle AOB, and then I could take it away from 180, and that would work it out for me. So angle AOB is 54.44. So the bearing must be 125.16. So 6C is a whole heap of trig questions, but now involves pictures with 3 dimensions. You might need to redraw some 2-dimensional pictures to make life easier for yourself.